Today's topic is about tree, binary tree, insertion, deletion, and traversal. So let's get into it. So first thing is tree. Tree can be anything. For example, it can be just a branch. It can branch out how many ever. It can have multiple branches. It can have more than many branches. This is the root. This is the root for everything else, and for these, this is the root. And for binary tree can only have binary tree can only have um, 0, 1, 2 branches. These are the maximum number of branches it can have. It can have 0, 1, 2 branches. So it can only look like this. It cannot have a third branch. This is fine. It cannot have a third branch. And it can only have a left and a right child. So basically it can only have left and a right child. Okay. And yeah, so, and the properties, let's see if the properties, if L is the maximum number of, so L equals to 2L, this is the equation to find maximum number of nodes at any level. For example, this is level 0, so it will become 2 raised to 0, which is 1. This is level 1, so it will become 2 raised to 1, 2. There are 2 nodes. And this is level 2, so which means 2 raised to level 2, that is 4. So this is one of the property. And then coming to the insertion, inversion and traversal of this. Like this is basically to how to design a tree. So how to design it is basically in the left side smaller node, or smaller node. On the right side, bigger node. So for example, if we have given with 4, 2, 3, 6, 5, 7, 1, and this 4 we will take as the main root, and then from 4 we check for 2. Is 2 after 4 we take 2. Is 2 bigger than 4? No, it is not, so it will come on the left side. And like that we go for the next one. We go for the 3. We done with 2, now we go for 3. So is 3 bigger than 4? But it is not, but it is bigger than 2, so we draw it on the right side. And like that over here we go with the next one. 6. Is 6 bigger than 4? It is, so we write it on the right side. Okay. And then after that we go with 5. Is 5 bigger than 4? It is, but it is smaller than 6, so we write it here. And then right like that we go for 7. Is 7 bigger than 4? It is, and it is bigger, it is 7 as well. It is bigger than 6 as well, so we write it on the right side. And like that this comes on this side. So this is how we design a tree. And that's how we design a tree. And to find the height of the tree, you can use the formula log equals n, where n is the, so the answer to this will be n equals to log 7. Now let's go to the deletion. Let's go to the deletion part. So deletion part is basically, if we have to check for if it's a tree with if it's a leaf node. Leaf node means with deleting leaf node, there is like literally only one, it is the last node. Like it's the last one. Okay, if this is the last one, you can simply delete it and nothing will happen. The order, nothing will affect if it's only 0. If there is more than one, if there is no leaf nodes, and then if there is like 1 or 2, then it is different. So if it's 1, then what we do is that, like for example 25, 10, 35, 40. For example, this has one branch attached to it. So if you want to delete this, what will happen? If you take this out, this will rearrange itself to 25, and it'll look like 25, 40, and then 10. It'll look like this. Okay. So, but like this is what you call. It'll just rearrange itself with no difference. But the problem is when there is 2. If it's 2, what will happen is, for example, we'll take an example here. If it's 25, 10, 20, 15, 21, and then 13. If you want to delete, and there is something else here as well, okay? If you want to delete this, 10, what we do is go to the right side and find the smallest element. Smallest element. So the right side and found the smallest element, which is 13, and we replace it with 10. So it will look like 25, 13, 20, 15, 21, and yeah, these 2 branches, whatever you can put them. 15, let's put 2, and we got, yeah, and then 15, and the 13 will come here, and that will delete itself. This is the deletion part. Now let's get to the tree traversal part. So tree traversal. So pre-order needs root, then left, then right. In order, in between, you can say left, root, right. Post order, left, right, root. Okay, this is the if you X, Y, Z, if it's like this, if you're going for pre-order, it'll become root, X, left, Y, and then Z, left, right. If you're going for in, then it'll look like left, root, right, left, root, X, right, then Z. If you're going for post, it'll look like Y, Z, X. So that is basically left, right, root. Okay, but this is an easy example. If you want to, if they ask a hard question, for example, I have a trick. So this is to find for pre-order, in-order, post-order. You can find this using easy trick. So I'll show you. So first let's make the nodes. So pre, in, and post. Let's name them as well. A, B, A, D, G, I, H, E, C. Okay, So now the trick is whichever does not have a which does not have another branch, you give them an extra branch. If they are missing a left branch, you give them a left branch. If they give them a right branch, you give them a right branch. So here, 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 and yeah, now everybody has a left branch and a right branch. And now what we do is we start from F. We start drawing a line from F. Okay, so first we go through F once. So we write F here, F, and then after that we go to B once. We reach B, A. So that means B, A. If we go through, if we go through once, then it's pre. If twice, then B, then sorry, then in. If thrice, then post. So if it's in, wait, now FB, FBA, FBA, we've gone through them twice, and this is the second time we come here. Okay, so there'll be A, and then after that one more time, this is the third time we reached, so then it becomes A over here as well, A. And then we go again, we reached B for the second time because we've already gone through it, so it becomes B. And then after that we go to D, which is the first time, D. Then we go to C for the first time, so C. Then we go through it once and thrice, twice and thrice, so C, C. And then after that we go through D for the second time, so D comes here. Then we go through E for the first time, then E comes here. And then we go twice and thrice, so E, E. Okay, then we go to D for the third time, so D. And then after that we reach B for the third time, that makes it B again. And then after that we reach F for the second time, which makes it F. And then after that we go to G for the first time, so makes it G, so it comes in pre. And then after that second time we go to G as well, G. And then after that we go to I for the first time, so we go I. And then after that we go to H for the first time, so that H. And then second and thrice, so H, H. And then we reach I again. And then after that we go again and we reach I for the third time. And then after that we reach G for the third time. And then after that we reach F for the last time. So and we finished the line. So this makes the entire, this is the answer for pre, in and post. And this is the trick to use, and if for complex structures we can use this trick. So thank you. Now we'll go to the coding part.
So now we are going to see the code for implementing insertion, deletion, and transversal operations in binary search. Okay, so coming to the code, first we open a class. First we open a class, class tree node. Okay, anything we can open class tree class tree node. And then after that we're going to define a function, initialization function. Is a function, then self key, self and key. And then after that we're going to write this is basically, this section defines a class tree node to represent a node in a binary search tree. It has like two things called left and right. First, now we're gonna write left and then right to store reference to the left and right child nodes respectively. Like it is going to the left side, it's going to right side, and a value to store the value of the node. Okay, so self dot left equals none. We're gonna store it as empty. None. Then self dot right equals none. Then we're going to give it a value to store the value of the node. Uh, key, key, key. Okay. Um, so the next part we are going to insert a function which is responsible for inserting a new node with a value key into the binary search tree rooted at root. Okay. So we're going to define another function. If root is none, if the root is none, then it will return a value, return tree node, tree node, return tree node and key. Okay. Um, Else if it's not empty, if the key, if the if key is greater root dot val, insert root left key. Otherwise else else root dot right equals insert root root dot right key. Otherwise return root. Return root. Otherwise return root and yeah and yeah. So this part was from here to here. This part was basically the function insert is responsible for inserting a new node with the value key into the binary search tree rooted at root. It recursively transfers the tree to find the appropriate position for insertion based on the value of the nodes. Okay. Now coming to the next part. The next part is basically this function mini value node. Like I'm going to define a function called mini value node, finds the node with the minimum value in the subtree. In the when it has a lot of extensions and a lot of subtrees, it is going to find the minimum value. It iteratively transverses the leftmost node in the subtree to find the minimum value. It is, I explained in the video previously that the um, like towards the left and towards the right it will show the highest value, and towards the left it will show the minimum value. So this code is to find the recursively find the smallest value. Okay, now let's write the code. The code is basically uh, definition. We're gonna open another definition function, define a function, mini value mini value node current node while current while current is not none. Current current none, this that, while current dot left is not left is not none. Okay. Now on to the next part. Now we're going to make a function called delete node. Deletes a node with the value key from the binary search tree rooted at root. Sorry, it handles the three cases: when the node is to be deleted and has no children, when the node has one child, or it has one child, when it has one child or it has two child. It recursively finds the node to be deleted and adjusts the tree accordingly. So let's write the program for that. So now we gotta define another function, define a new function. Mm, so a definition delete node, we can name it delete node root key if the root is none, then return the root. So where was I? If the key root val root dot left equals to delete node dot left key elif function we use if it's another case. That's why we use elif function. Elif, if the root key value is greater than the root value, is greater than the root value, then return root right root right root right equals to this, and delete node root right. Okay, and then if it's the other one, delete node root right key else if root dot left is none. Is none. Then return temp. Elif root elif root uh, is none. Right root right is none. Root right is none. Is none. None. So if elif root is none, temp temp root root left root temp is root not left. Return temp then temp equals to mini value node, mini valued mini value node. Root dot write root val temp val and then root right the delete node. Delete node with root right or temp val. Root return root. So now this was the definition. I mean, this was the code for delete node. Now we have the code for transversal, in order transversal, which performs in order transversal at the binary search of the root. So let's do that as well. So for that we make we define another function definition. Then we write in order transversal traversal, in order traversal root if root in order traversal print root val and in okay. Now this was the code for in order traversal. Now we can just need to give the root value. We have to sort of root insert root value and then we can print for in order transversal, we can delete, we can do that. So first, as you can see, I've written the code for in order traversal. So first, we what we do is that we open a class. This that line defines a class named tree node. It represents a node in the binary tree basically. And then after that, we have defined a function and initialized it with the constructor method in it, and then after that it initializes a new code with a given value with key. Okay, and then after that, inside the constructor inside the constructor, left references to left child node, right references to right child node, and val stored is equals to val stored in the node. This is the value stored in the node. And then after that, we have defined another function in order traversal that performs an in order traversal of the binary tree. And then after that, the if root, this line checks if the current node exists and is not none. If it exists, the code inside the if is the block executed. If it is, the line recursively calls the in-order traversal function on the left subtree of the current node, and then this print root value. This line prints the value of the current node. Okay, it prints the value of the current root. The end parameter specifies this one. The end parameter specifies that it should be end of the print statement. By default, it's a new line character /n if you know, and it is overridden with a space. And then this line recursively calls the in order traversal function on the right subtree of the current node. And yeah, and this is executing we're giving values to it, and this when we print it, it's gonna do the in order traversal of this. It's gonna perform in order traversal, and it's gonna look something like this tree right here. I have written it in comments. So thank you for watching my lecture. Have a nice day.